Section 4.3. How do derivatives affect the shape of a graph? This section is essentially asking, what does f prime say about f? What does the derivative tell you about the original function? We started to investigate this in an example in the previous section. If we recall that the derivative models the slope of a graph at all points along the graph, we can see that if the derivative f prime is less than 0, then the function is decreasing because the slope would be going down and to the right. On the other hand, if the derivative f prime is greater than 0, then the function is increasing, and if f prime is equal to 0, then it must be a turning point. Now we are able to prove that all of this is true. So first we have what is called the increasing-decreasing test. If the derivative is positive, so f prime of x is greater than 0, on an interval, then f is increasing on that interval. If the derivative f prime of x is less than 0 on an interval, then f is decreasing on that interval. The proof for this is exactly the same as what we saw at the end of the previous section. So as an example, find where the function f of x equal to 3x to the fourth minus 4x cubed minus 12x squared plus 5 is increasing, and also where it is decreasing. First we start by finding the derivative. F prime of x is equal to 12x cubed minus 12x squared minus 24x. And for the purposes of what we need, it becomes helpful if we actually factor this. And this factors to 12x times x minus 2 times x plus 1. So what we want to figure out is where's the derivative positive and where's the derivative negative. To do this, it becomes a little bit helpful to organize just using sort of a chart. And the way that this chart works is we have three factors from the derivative: 12x, x minus 2, and x plus 1. What we can use are the zeros of those factors, meaning f prime of x is equal to 0 when those factors are equal to 0. So when x is equal to negative 1, because that's when x plus 1 is equal to 0, when x is equal to 0, because that's when 12x is equal to 0, and when x is 2, because that's when x minus 2 is equal to 0. So just thinking of reading from left to right, we're dividing up this chart where the derivative is equal to 0. And then what you have in front of you are just intervals. So for example, on the far left, this would be the interval from negative infinity all the way to negative 1. And then the next interval would be from negative 1 to 0. And then from 0 to 2, and then from 2 to infinity. And so what we're going to do is just figure out, is our derivative positive or negative in each of those intervals? And then that's also going to tell us something about the actual function, f of x. To accomplish this, we can just use a test point. So for each interval, we can just think of a number that's in the intervals. So for example, the interval negative infinity to negative 1, I just need some number that's in that interval. I could choose anything I want, like negative 1,000 if I wanted to, but it might be a little bit easier if we use some smaller numbers. So how about x equal negative 2, because that's in that interval. The next interval, a test point that I could use would be x equal to negative 1/2. The next interval, some number that's between 0 and 2. Again, I could choose a really complicated number like 17 over 16, but how about I just choose something like x equal 1. And then for x equal 2, some interval past that from 2 to infinity, an easy number there would be x equal 3. So this just takes a little bit of work on the side, and we're just taking those numbers, what I wrote in red, and putting it into our derivative, the 12x times x minus 2 times x plus 1. And it helps if we just think of those factors. So would they be positive or negative? So for example, If I think of my three factors, 12x, x minus 2, and x minus 1, and I plug in x equal negative 2 into x, I would get a negative from the first factor, because 12 times negative 2 is negative 24. If I plug in negative 2 to the second factor, negative 2 minus 2 is negative 4, so that's another negative. And then for x plus 1, negative 2 plus 1 would be negative 1. That's another negative. A negative times a negative times a negative, that is a negative. So that means that f prime of x is negative or less than 0. This then tells me that my function, f of x, that's increasing. This then tells me that my original function, f of x, is decreasing in that interval. So let's continue that with the others. If I take x equal negative 1/2 and put it into the first factor, I would get negative 6, so that's a negative. If I take negative 1/2 and plug it into x minus 2, that's another negative. But when I take x equal negative 1/2 and put it into the third factor, negative 1/2 plus 1 is positive 1/2. And now I get negative times a negative times a positive. That's a positive. And so this tells me that my original function is increasing because the derivative is positive on that interval. So finishing up the rest, if I plug in x equal 1, I get a positive from the first factor, but I get 1 minus 2, which is negative 1 from the second factor, and then 1 plus 1, which is 2 from the third. This gives me a negative, so this means that my original function is decreasing. And in my last interval, when I plug in x equals 3, 12 times 3 is positive, 3 minus 2 is positive, and 3 plus 1 is positive. So this is just positive times positive times positive, which gives me a positive. So now I know the intervals where the function is increasing or decreasing. So I can organize this in my final answer. For increasing, I have the intervals negative 1 to 0, union, meaning the combination of both of these intervals, to infinity. And then for decreasing, I have negative infinity to negative 1, union 0 to 2. We're going to do more of this chart organization work as we get to another example later in this section. We learned a way to find critical numbers in section 4.1. Now we have a way to test those critical numbers to see if they give rise to maximum or minimum. You can already see a hint of this in the previous example. So now we have what's called the first derivative test. Suppose that c is a critical number of a continuous function. A, if f prime changes sign from positive to negative at c, then f, the original function, has a local maximum at c. Part B, if f prime changes sign from negative to positive at c, then f has a local min at c. And then thirdly, if f prime does not change sign at c, then f has no local max or min at that critical number c. So let's see an example of this. Consider the function f of x equal cosine squared x minus 2 sine x over the interval 0 to 2 pi. Part A, find the intervals on which f is increasing or decreasing, so just like the previous example. And then part B, find the local max and min of f. So first of all, to find the derivative of cosine squared x would be 2 cosine x, but then by the chain rule times the derivative of cosine, which is negative sine. So that's why we get negative 2 cosine x sine x. And then minus the derivative of 2 sine x is 2 cosine x. I can factor out a 2 cosine x from both terms, and I would have 2 cosine x times negative 1 minus sine x. So as we saw from the previous example, I need to first figure out where is f prime of x equal to 0. And notice this is going to tell us our critical numbers. So f prime of x is equal to 0 when 2 cosine x times negative 1 minus sine x is equal to 0, which means 2 cosine x equals 0 and negative 1 minus sine x equals 0. So then this turns into cosine x equal to 0. And then from negative 1 minus sine x equal to 0, this turns into sine x equal to negative 1. So then the cosine function, if I'm looking at the interval from 0 to 2 pi, this is equal to 0 when x is equal to pi over 2 and 3 pi over 2. And then sine x is equal to negative 1 when x is equal to 3 pi over 2. So my critical numbers are just pi over 2 and 3 pi over 2. So just like in the previous example, I'm going to set up a chart where I've split up the real numbers using my critical numbers. This is what we were doing in that previous example. So I have pi over 2 and 3 pi over 2. And we also can split this up by just remembering that our interval originally just went from 0 to 2 pi. So I'm really just focused here. And again, we're going to be looking at some test points. So some numbers in each of those intervals, and then put those into our derivative to see if we get positive or negative. And then we can put this all together to find out where's our original function increasing or decreasing, and then also see if we have any local max or min. So for some test points, between 0 and pi over 2, I can use pi over 4. Between pi over 2 and 3 pi, I can use pi. And then for a number between 3 pi over 2 and 2 pi, I can use something in quadrant 4, so 7 pi over 4 will work. So now I'm going to take these critical numbers and plug them into my first derivative to see if I get negative or positive, and then that'll tell me something about my original function, f of x. And I can get those intervals where the function is increasing or decreasing, and then also try to identify any local max or min. So first, I'll take the first derivative, and I'm going to plug in pi over 4. And so my first derivative evaluated at pi over 4, that would give me 2 times cosine of pi over 4 times negative 1 minus sine of pi over 4. Cosine of pi over 4 and sine of pi over 4 are both square root of 2 over 2. So this gives me square root of 2 after multiplying by the 2, and then negative 1 minus square root of 2 over 2. Whatever is in parentheses, whatever that's going to be, I don't really care. I just now can see that I have a positive times a negative, which is going to be less than 0. So my first derivative is negative in that interval from 0 to pi over 2, which means my function is decreasing. And then from pi over 2 to 3 pi over 2, I'm going to plug in pi as my test point. This gives me 2 times cosine pi times negative 1 minus sine pi. Cosine of pi is negative 1. When I multiply that by 2, I get negative 2. And then sine of pi is 0, so negative 1 minus 0. That's going to be a negative times a negative, which is positive. So this means that my function is increasing now. And then finally at 7 pi over 4, cosine of 7 pi over 4, that's going to be square root of 2 over 2, but then times -1 minus sine of 7 pi over 4, that's going to be a negative. So this turns into square root of 2 times -1 minus negative square root of 2 over 2, which is -1 plus square root of 2 over 2. And square root of 2 over 2 is greater than 1, so this is going to turn into a positive times a positive, which is greater than 0. So I could still have increasing on that interval. So now I can summarize what I just got from all of this. My intervals I can write down first to answer part A. So I can say decreasing, that's on the interval 0 to pi over 2. And then increasing, I can say from pi over 2, and that goes all the way up to 2 pi. And I can also answer for part B, what happens at the one sign change. I notice that I'm changing from a negative first derivative to a positive. So that means I'm going to have a local minimum according to part B of the first derivative test. So I have a local min at x equal pi over 2. So that's the location. If I want to know the value, I should plug in pi over 2 into my original function. So the value of my local minimum would be f of pi over 2. And if you plug pi over 2 into your original function, cosine of pi over 2 is 0, and then sine of pi over 2 is 1. So this gives me 0 minus 2, which is -2. We have 2 more tests to finish up in this section. We saw how to determine increasing or decreasing, and also how the first derivative test helped us find local maximum and minimum. Now we look at what's called the concavity test, which describes how a function may be increasing or decreasing. Before that, first 2 definitions. If the graph of f lies above all its tangents on an interval, then it is concave upward. If f lies below all its tangents on an interval, then it is concave downward. So this may seem like a complicated definition, but we actually saw something with this with earlier examples. Like concave up really just means like this. It's a graph that's opening up. And if you think about the tangents, they would be below the graph. Whereas if you have concave down, then this is the second sentence of the definition. That graph is below all of its tangents. So this is just relating the graph to its tangent lines. Really, when I think of these definitions, I just think of curving up or curving down. That's how I think of concave up or down. So now, if you look at concavity, you can make some inferences about the tangent lines. For example, if on an interval the function is concave down, say before a maximum, so like at the graph I have here at the top, if I just think of looking from the left up to the top of the graph, then its tangents will be positive. You can see that they're going up and to the right, but as we reach the top, they start to get shallower. Thus, on the graph of the first derivative, the slopes would be decreasing. They're getting smaller. Then on the same interval, f prime is decreasing. We just learned that there's a strong relation between a decreasing function and its derivative being negative. So it stands to reason that f double prime, the second derivative, is negative on that interval. A similar argument works for where the function is concave up. This all leads to the concavity test, which summarizes that previous paragraph. Part A, if the second derivative of f of x is greater than 0 for all x in an interval, then f is concave up on the interval. Part B, if the second derivative of f of x is less than 0 for all x in an interval, then f is concave down on the interval. The point where a function changes concavity is called an inflection point. There will be an inflection point wherever the second derivative changes sign. Let's see an example of the concavity test by continuing from our previous example. We're going to find the intervals of concavity and inflection points for that previous function. So that previous function was f of x equal to cosine squared x minus 2 sine x. And then we said that f prime of x was equal to negative 2 cosine x sine x minus 2 cosine x. So then our second derivative, we'd first use the product rule on negative 2 cosine x sine x. That would give us positive 2 sine x times sine x, and then minus 2 cosine x cosine x, and plus 2 sine x. And we can arrange all of this together as 2 sine squared x minus 2 cosine squared x plus 2 sine x. Just like the previous example, to figure out the intervals of concavity, we first need to figure out where is the second derivative equal to 0. So this is kind of like finding the critical numbers of the first derivative. So this means I have 2 sine squared x minus 2 cosine squared x plus 2 sine x equal to 0. This is a very typical trigonometric equation. It's quadratic in form, which means you're going to have to do something that involves factoring and then setting factors equal to 0. The first thing that I can do is divide every term by 2, because 2 is a common factor in every single term on the left. This leaves me with sine squared x minus cosine squared x plus sine x equal to 0. And then I want to get everything in terms of one trigonometric function to make this easy. So I'm going to have everything in terms of sine x. To do that, I need to use the Pythagorean identity on cosine squared x. So then I have sine squared x minus, and instead of cosine squared x, I'm going to write 1 minus sine squared x. And then plus sine x equals 0. Combining like terms, I will end up with 2 sine squared x plus sine x minus 1 equals 0. And then factoring, I would have 2 sine x minus 1 times sine x plus 1 equals 0. And then I'm going to set my factors equal to 0. So 2 sine x minus 1 equals 0. That means that sine x is equal to 1/2, which means that x is equal to pi over 6 in quadrant 1 and 5 pi over 6 in quadrant 2. So I'm going to need those two. And then my other factor, sine x plus 1 equals 0, means that sine x is equal to negative 1, which means that x is equal to 3 pi over 2. So that's another number that I'm going to need. Just like I did in the previous example, I'm now going to set up a chart using these numbers to split up my interval. So the interval that we had was from 0 to 2 pi. And the numbers that I'm using to split this up are pi over 6, and then 5 pi over 6, and then 3 pi over 2. You don't have to space this out like it would be on the number line. You're just trying to have some way to organize this. And so then we are trying to see where is our second derivative, positive or negative, and then that will tell us something about, again, our original function, whether it's concave up or concave down. So again, we're going to need some test points. For some test points that you can use, the first interval is a little bit tricky because you have 0 to pi over 6 or 0 to 30 degrees. So you can just choose something that's less than that, whatever you want to think of. I don't know, pi over 12, which would be 15 degrees. And then between pi over 6 and 5 pi over 6, just think what's splitting up quadrant 1 and quadrant 2. pi over 2 is a really easy one to use. Between 5 pi over 6, which is in quadrant 2, and then 3 pi over 2, pi is an easy number. And then finally, between 3 pi over 2 and 2 pi, we can use, again, something that would be in quadrant 4. So like 7 pi over 4. So to use our test points, we are going to need our second derivative again. And I need to use the form before I started solving it, which was 2 sine squared x minus 2 cosine squared x plus 2 sine x. So before all of my equation work, just what I have circled up here. So then if I plug in pi over 12 or 15 degrees, if you want to use degrees, you can check this with a calculator, is probably the easiest way to do that. You're going to get negative 1.214. So that is less than 0. And since we get a negative for that interval, that means that f of x would be concave down. If I do the same thing with pi over 2 for the next interval, sine of pi over 2 is 1, cosine of pi over 2 is 0. So I get something that's positive. So I get concave up. And then for the next interval, second derivative evaluated at pi, sine of pi is 0, cosine of pi is negative 1, but negative 1 squared is 1, so this still turns into minus 2, and then plus 0, that's negative 2, which is less than 0, so I get a negative, so I get concave down for the next interval, and then finally the second derivative evaluated at 7 pi over 4. Sine of 7 pi over 4 would be negative square root of 2 over 2, but then I'm squaring that, so that's 2 over 4 times 2, that's just going to be 1. You're going to get the exact same thing for 2 times cosine squared, so that's 1 minus 1, and then I would have minus, because 2 times negative square root of 2 over 2, minus square root of 2, that's negative square root of 2, which is less than 0. So we have concave down for that last interval. So summarizing all of this, we can see our intervals where the function is concave down. As the intervals 0 to pi over 6, union 5 pi over 6, and since it goes all the way through to 2 pi, we can say all the way to 2 pi. And then concave up, there's just one interval for that. That's from pi over 6 to 5 pi over 6. Inflection points happen when there's a change in concavity. So there's an inflection point at pi over 6 and also at 5 pi over 6. And just like we did with maximum and minimum, we should plug those into our original function to see what the values are. So the original function evaluated at pi over 6, again going back to our original function, cosine squared x minus 2 sine x, cosine of pi over 6 squared minus 2 times sine of pi over 6. Cosine of pi over 6 is square root of 3 over 2. When we square that, we get 3/4. And then sine of pi over 6 is 1/2. So this will be 3/4 minus 1, or negative 1/4. And then f of 5 pi over 6 pretty much will give us the same result. Since cosine of 5 pi over 6 is negative square root of 3 over 2, but when I square that, I get, again, 3/4. And sine of 5 pi over 6 is 1/2, so this becomes 3/4 minus 1 again. So now we have where the inflection points happen and what are the actual function values for those. And then finally, a consequence of the concavity test, and this is called the second derivative test. Suppose the second derivative, f double prime, is continuous near c. If the first derivative, f prime of c, is equal to 0, and the second derivative is greater than 0 at c, then f has a local max at c. Part B, if the first derivative, f prime of c, is equal to 0, and if the second derivative at c is less than 0, then f has a local minimum at c. This gives the same result as the first derivative test, but there are times where the second derivative test can fail. For example, when the second derivative is equal to 0, we wouldn't get any information out of that. So it's an alternative. I wouldn't say that it's better. If all you are after to find is to find the local max or min, the first derivative test would be the easier one to use. And then we can put all of these tests together, just like we did in the previous examples, to sketch a graph. So we're going to do another example, but with a slightly easier function to consider. Sketch a graph of f of x equal to x to the fourth minus 4x cubed, describing the location and values of the local maxima, minima, and inflection points, and also describing the intervals of concavity and intervals where the function is increasing or decreasing. So this is essentially just like we were doing with the previous examples, just with a new function. So we know certain things that we're going to need to find, like the first derivative, and then the second derivative. So our first derivative, f prime of x, that's equal to 4x cubed minus 12x squared. And then we need to find the critical numbers for f of x just based off of the first derivative. So I set f prime of x equal to 0. And I can factor and get 4x squared times x minus 3, which means that x equals 0 and x equal 3 are my critical numbers. And so right here I can at least start answering questions about increasing, decreasing, and maxima or minima. So I'm going to split up my number line here. I am looking at all real numbers, so I have numbers before x equals 0, and then numbers between 0 and 3, and then numbers greater than 3. So I need some test points. So for anything before x equal to 0, I'm going to use x equal negative 1. For a number between 0 and 3, how about x equal positive 1? And then for numbers greater than 3, x equal to 4. So keep in mind what we're trying to do here. I'm using these test numbers, the ones that are in red, and I'm putting those into my first derivative to see if the first derivative is positive or negative. Once I have an answer about that, then I know if my function, f of x, is increasing or decreasing. So testing at my test points, f prime of negative 1, this would be 4 times negative 1 cubed, which is negative 4. And then minus 12 times negative 1 squared, so negative 4 minus 12, that gives me negative 16, and that's less than 0. So the first derivative is negative in the interval leading up to x equals 0, which means that my function is decreasing on that interval. Then continuing, evaluating the first derivative at 1, this just gives me 4 minus 12, which is negative 8, which is also less than 0. So it's still decreasing. And then finally, the first derivative evaluated at 4. This would give me 4 times 4 cubed. So that's just going to be 256. and then minus 12 times 4 squared, so minus 12 times 16. And we can see that we're going to get a positive. 256 minus 192 gives me 64. So positive, so the function does go back to increasing. So we can answer a couple of questions so far. Intervals of where the function is increasing or decreasing. So we can say decreasing. That's on the interval all the way from negative infinity to x equal 3. And then increasing that's from 3 to infinity. And we can also state the one place where we have a change in sign in the first derivative. So f prime of x changes from negative to positive. We saw that before. When it changes from negative to positive, we get a local minimum at x equal 3. So the value, now notice here I have to use my original function because I now want to talk about what value the original function has at this minimum. That would be f of 3. So this would be 3 to the 4th power, or 81, minus 4 times 27, which would be 108. So I get negative 27. Okay, and if you think about what we've done so far, maybe consider the original function is a polynomial with an even degree and a positive leading coefficient. So we know that this should be opening up. So if you look at this from left to right, it goes down first, hits a local minimum at some point, and then heads back up. So we're just reiterating that here. We could have done some of this in pre-calculus, but we couldn't have known where the minimum might actually be. We would have taken a guess. Now we actually know. So then to keep going, we want to answer questions about concavity. So now we need the second derivative. So my first derivative was 4x cubed minus 12x squared. The second derivative would be 12x squared minus 24x. And again, I need to set the second derivative equal to 0, which means I would have 12x squared minus 24x equal to 0. Solving for x, I get x equals 0 and x equal to 2. So then I'm going to split up my number line again using 0 and 2. And now I'm considering what happens to my second derivative. And then that tells me something about my original function, f of x. I'll again use some test points. X equal negative 1 works again. X equal 1 and x equal 3 I could use again. Or since that was a critical number, if I don't want to confuse myself, how about x equal 4 again? And again, I'm plugging these into my second derivative. So I have to take the second derivative at those test points. So the second derivative at negative 1, that would be 12 times negative 1 squared, so 12, minus 24 times negative 1, that's a plus 24, that's 36, which is positive. And since I'm saying that my second derivative is positive, that means by the concavity test that my original function is concave up. And then my second derivative evaluated at 1, that would be 12 minus 24, which is negative 12, which is negative. So that means I have concave down. Now I can see that since I have a sign change there, there's going to be an inflection point at x equals 0. But finishing at least our intervals of concavity, the second derivative evaluated at 4, that would be 12 times 16 again, 192, and then minus 24 times 4, 96, which is 96 or positive. So it goes back to concave up. So I've got another inflection points. So intervals of concavity, we can say concave up. That's from negative infinity all the way to 0, and then union from 2 to infinity. And then concave down, that's just from 0 to 2. And then for those inflection points, those happen at x equals 0 and x equal 2. So I need to find f of 0. Going back again all the way to my original function, plugging in 0, that would just give me 0. So at the origin, I have an inflection point. And then at x equal 2, I need to plug in 2 to my original function. So 2 to the 4th, 16, minus 4 times 8, that would be negative 16. So that's another inflection point. So now let's put this all together in a graph. I've got some points for my inflection points, 0, 0, and 2, negative 16. I also have a point for my local minimum, which was 3, negative 27. So I'm just going to use those points as some reference. So I need a y value as far down as negative 27. I also need something with a negative 16. So I'm going to count by 4s here. Negative 4, negative 8, negative 16, negative 20, negative 24, negative 28. And then for my x values, I just need not too many numbers, so 1, 2, 3. So I'm going to plot some of those points that we had. We had 0, 0 as one of the inflection points. We also had 2, negative 16 as another inflection point. And then we also had 3, negative 27 as our minimum. We could do a little bit more with points by finding the zeros where this function crosses the x-axis. We already see one of them. But just from what we already learned from the increasing, decreasing, and concavity, we can complete the graph. So notice from negative infinity to 0, we have decreasing. And also from negative infinity to 0, we have concave up. So what that tells us is that we have something where if you follow from left to right, it's going down, but it's staying concave up that whole time. But then once it crosses 0, the concavity changes between 0 and 2. But then between 0 and 3, it's still decreasing. So I have to change this concavity just slightly so that it appears to be concave down, which is kind of like in an x cubed graph, where you're still decreasing, but it is changing concavity just slightly. That goes all the way to x equal 2, but then we switch concavity at that point. It now goes to concave up, still decreases all the way to x equal 3. Concavity is just slightly up, and then once it hits that point, then it goes back up again. And then we know at some point it is going to cross the x-axis, but we're not really concerned with where at that point.